All right, so we are factoring degree 3 and degree 4 polynomials. And so when you factor, the goal of factoring is to get everything in terms of linear factors. And so when we were factoring quadratics, that is a degree 2 polynomial, our goal was to get 2 linear factors. We just did that on the warm-up 5 times. Okay, if we factor a degree 3 polynomial, our goal is to get to 3 linear factors. And then if we are factoring a degree 4 polynomial, we are looking for 4 linear factors. Again, that's the goal. Sometimes we're going to be stuck with a quadratic factor in there that is not factorable, and that's okay. That's why you need to be able to recognize, is this quadratic factorable or not? And so the Algebra 2 standard says degree 3 and degree 4. We have some degree 5s and some degree 15s on here. Don't worry about that showing up. It's just so you can practice the method in depth. Okay, so the first method we're going to talk about is factor by grouping. And so half the battle with factoring is recognizing which of the special cases it is. And so a factor by grouping case would mean there are 4 terms. Anytime you have 4 terms, you're going to try to factor by grouping. Can you move away from him because you can't seem to stop talking to him? Okay, so 4 terms. The other thing that you have to have is the ratio of first 2 terms has to equal the ratio of last 2 terms. And you don't actually have to check that that's true. You can just try to factor by grouping, and if it doesn't work, then look and see, oh, it's because the ratio didn't work out. Okay, and so looking at number 1, there's 4 terms, so I'm immediately thinking, okay, factor by grouping. And so if you look at the ratio of the first 2 terms, our first term is 3x cubed. Our second term is x squared. If I simplify this fraction, it simplifies to 3x. If I look at the second 2 terms, the first one is negative 3x over negative 1. That also simplifies to 3x. And so the ratio works. Okay, just showing you how that ratio goes. And so I know factor by grouping will work. And so you factor this just like we did the quadratics, only it's even easier. You don't have to find the magic numbers because you already have 4 terms. And so you just draw your line right down the middle. Don't cut off that sign because you need it. And then out of the first 2, we can factor out an x squared. And then that leaves behind a 3x plus 1. Out of the second pair, we're going to copy down that minus sign. There's nothing else in common, so we have to write a 1. Not 0, 1. Okay, and so we're factoring out a negative 1, which leaves behind a 3x plus 1. Love this method because if this matches, these parentheses match, we've done everything right. Okay, and so 3x plus 1 is our first factor, and x squared minus 1 is what's outside the parentheses. They come together to form our second factor. Okay, and so before we box our final answer, we have to make sure we've got linears. And so this first factor is linear, and there's no numerical GCF, so that one's good. This second factor is quadratic, and so I don't want to leave this like that unless it's unfactorable. This is factorable. It's one of our difference of squares. 1 is a perfect square, 1 times 1. And so this is a difference of squares, so we can factor that to x plus 1 and x minus 1. And then the 3x plus 1 goes there. All three of these linear factors are in parentheses, so you would be able to type these in any order, and it would be correct. Okay. Before I move to the next question, if I'm taking a test or a quiz or even just making an answer key for you guys, I always multiply the first term of each factor, which would give us 3x cubed, and make sure it matches the original. Okay, that's going to help you not forget GCFs. Okay, so just quickly multiply the first two terms, see if you get the original first term back. If you forgot a GCF, you would catch that mistake right there. Okay, moving on to number 2. We've got 4 terms, so I try to factor by grouping. Draw a line right down the middle. I'm definitely going to have an x squared in common, and also a 2 between the 10 and the 6. Okay, so if I factor out a 2x squared, that leaves a 5x minus 3. To the next pair, we copy down that plus sign. And then there is nothing else in common between a 5x and a minus 3, so we put a 1. Need that 1. Okay, so if we factor out a 1, we still have a 5x minus 3 sitting there. And so our parentheses match. We're doing everything right. 5x minus 3 is one of the factors, and then the other factor comes from the 2x squared out front and this plus 1. Okay, 5x minus 3 is a linear factor, and there is no numerical GCF, so that one's done. And so now I'm looking at this quadratic. We have a plus sign between this x squared term and this constant, so it's definitely not even going to be anything we could factor. Even if they were both perfect squares, sum of squares is not a thing. So even if that 2 was a 4, still wouldn't work. So not factorable. Explain why this isn't factorable. Yes. The only way we could factor a quadratic with 2 terms is if it was a difference of squares. Okay, and so even if I had a perfect square here and a perfect square here, if there's not a minus sign between them, still not factorable. So this is not factorable. Okay, watch out for that. Sum of squares is not a thing. Yeah. Nope. Like 4x squared plus 25, x squared plus 1, not factorable. Yes, there would be a numerical GCF. So his question was, if you saw a 2x squared minus 4 sitting there, you would definitely want to factor out the 2. And then you would be done. X squared minus 2 is not a perfect square, and so you would be done at that step. If there is a new numerical GCF in one of your factors, that just means there was a numerical GCF from the very beginning. And so you could do it at the beginning or the end, just don't leave it. And so that's why I want to train you to check at the end for numerical GCFs as well, even though you're checking at the beginning. Okay, and so we box our final answer. And before we click submit, we're going to multiply the first 2 terms, 5x times 2x squared. And that would give us 10x cubed, which is our first term. That's just a quick check for you. Okay, number 3, I put this on here, or Mr. Davidi put this on here. There's 5 terms here. And so it is not a factor by grouping case. And so can't factor by grouping. Our special cases only apply to 4 terms, 3 terms, or 2 terms. If you have 5 terms, it's not a special case. There's a different method for factoring those that we'll get to next time. It requires synthetic division. And so we're going to leave that alone for now. Okay, number 4 is on here. It's degree 5, but really, there's a GCF. Always look at your last term, and if your last term is not constant, that means you have a variable that you can factor out. In this case, we can factor out an x squared right off the bat. And so when you do that, when you're factoring out x squared, it's going to drop every exponent by 2. Okay, so really we have an x cubed plus 3x squared minus 2x minus 6. So now we're back to an algebra 2 problem that's a degree 3 polynomial. There's 4 terms, so we can draw our line right down the middle and factor by grouping. Okay, the first pair has an x squared, leaves behind an x plus 3. We can copy down that minus sign. And then they also have a 2 in common, leaving behind an x plus 3, just like we wanted. Okay, and so x plus 3 is one of my factors. X squared minus 2 is the other factor. And do not forget your GCF. Bring him back for the final answer. Okay, and so looking at what we have, this is a single term, so of course you can't factor that. This is linear. Love that. There's no numerical GCF. And this is not a perfect square. And so we're done with x squared minus 2. Box it. And before we click next, we're going to multiply x squared times x squared, which gives us x to the 5th. And that is our first term. Okay, so if you see 4 terms, try to factor by grouping. If it fails, see if the ratio worked out. Because sometimes 4 terms isn't a special case, and that's when we'll use synthetic division next time. All right, next special case is when there are 3 terms. Okay, so if you see 3 terms, there's 2 other criteria you need in order to use what's called EU substitution. And how do I want to say this? First and second exponent is 2-to-1 ratio. Basically, the first exponent has to be twice as much as the second. Okay, so here on number 1, we have a 4 and a 2. And then here we have a 6 and a 3. And so that's how you're going to know this is a U substitution case. Oh, I'm not on screen. 6 and a 3. Okay, the last criteria is last term is constant. Okay, so here we have just a 9. Here we have just an 8. And so 1 and 2 scream U substitution. And so what U substitution does is it turns whatever polynomial you're working with into a quadratic. Okay, and so how you're going to define U is you're going to set U equal to the middle variable. And so here there's an x squared there. And so I'm going to set U equal to x squared. Meaning I'm going to substitute every x squared with a U. Just like if in like a volleyball or basketball game, you sub a player out, U goes in for x squared. And so this x4, I can rewrite x4 as x squared squared. The rules of exponents, if you have 2 exponents on one base, you would multiply them together to give you back that x4. And so if I write that, I'm seeing x squared, get the ugly green highlighter. I'm seeing x squared twice in this problem. Right here, right here. He's getting subbed out of the game. U is going in. And so this problem turns into U squared minus 10U plus 9. And so now we can factor it just like we did our quadratics. Okay, and this a is 1, so we can even use the shortcut here. And so I'm looking for two numbers that multiply to 9, but add to negative 10. Negative 1 and negative 9. And so this quadratic factors to u minus 1 and u minus 9. Now don't box that as your final answer. Don't leave u there. He's just a placeholder. We have to put the x squared back. Okay? And so this turns into x squared minus 1 for our first factor and x squared minus 9. Is x squared minus 1 factorable? It's a difference of squares. What about x squared minus 9? Also a difference of squares. And so don't leave those. You can put the plus first or the minus first. We have 4 linear factors, all in parentheses. No numerical GCFs. That would be your final answer. Okay. And then if we multiply the first terms, x times x times x times x is x to the 4th. That's what we started with. All right, coming over here, I see a 2 out front. So I'm immediately going to look and see if 2 goes into the other numbers, and it does. So we're going to factor out that numerical GCF right off the bat. If you forget this, you'll still be able to do it at the end. It just makes your life a lot harder. Okay, and so factor out that numerical GCF. That leaves x to the 6 plus 4x to the 3rd plus 4. Okay, we're going to ignore the 2 for now, but don't forget about him for the final answer. All right, and so here we've got 3 terms. Last term is constant. First term has an exponent that is twice as much as the second. That screams u substitution. So what do I want to define u to be this time? X cubed. Okay, that way we have a 4u sitting right there. And so x to the 6 is the same as x to the 3rd squared. Remember, you multiply those exponents together, that would get you right back to the x6. That's why we need that 2-to-1 ratio. Okay, and you don't even have to write this step. You can immediately go to u. I just want to do this for your notes. Okay, so we've defined u to be this x to the 3rd, and we have x to the 3rd sitting right here and right here. He's getting subbed out of the game. U is going into the game. So now we have a beautiful quadratic where a is 1. We can use our a equals 1 shortcut. I just need 2 numbers that multiply to 4 but add to 4. 2 and 2. Okay, so that factors to u plus 2 and u plus 2. Don't leave u in the final answer. We got to replace it with that x cubed. So x cubed gets to go back in the game. And don't forget our 2 from the very beginning. These are unfactorable cubic polynomials. If that 2 was a perfect cube, we would be able to factor it even more, but you're not going to have to do that until the back. These are unfactorable, so just box it. You are done. Double check. 2 times x cubed times x cubed gives us 2x to the 6th. So we did everything great. Multiplying would help us find out that we forgot our GCF at the end. All right, let's factor this degree 15 polynomial. This is more like what you're going to see on the test, a degree 4 and like number 4. And so This degree 15 is just to really make sure you understand how U substitution works. Okay, so right off the bat, I see a numerical GCF of 2. I also see that this last term is not constant. We can also factor out an x. Okay, so 2x is our GCF here. Leaves behind x to the 14th minus 5x to the 7th plus 6. Okay, ignoring the 2x for now, we'll bring him back for the final answer. We have a 3-term polynomial with a constant, and the first exponent is twice as much as the second. That screams U substitution. What am I going to define U to be? X7. Good. And leave the coefficients out of it. The numbers don't get to be a part of it. Okay, and so that first term, x14, is U squared minus 5U plus 6. We can use the a equals 1 shortcut as long as we find two numbers that multiply to 6 but add to -5. Okay, so be careful with -6 and 1. Those do add to -5, but they multiply to -6. So we actually have to do -2 and -3 for this one. This one's like the ones, if this was a minus sign in front of the 6, we would want the magic numbers to be -6 and 1. But since 6 is positive, both of them have to be negative. So -2 and -3 are the only ones that work. Okay, so U minus 2, U minus 3. Don't leave that in your final answer. We got to put the x7s back. And those are not factorable, by the way. And then bring the GCF back for the final answer and put a box. (2x times x7 times x7 would get us back to 2x15, so we did it right. All right, number 4 and number 1 are the most similar to your test questions because they're degree 4, and that is the Algebra 2 standard. And so number 4 is an example where a isn't 1, so we can't use that shortcut, but we can still do it. So we've got 3 terms. The last term is constant. First exponent is twice as much as the second. That's how we know we can use U substitution. What does U equal here? X squared. Okay, and so leave that 4 out of it. That 4 is the coefficient. You still have to write him, but x4 is the same as U squared. Minus 21U plus 5. So all your coefficients from the original problem should still be there. Some people notice that 4 is a perfect square, but we didn't define U to have any numbers, so don't do anything with that. All right, so there's no GCF here, and so we need 2 numbers that multiply to A times C, which is 20. 4 times 5 is 20, but add to -21. -20 and -1. Okay, do not write U minus 1 and U minus 20. Shortcut does not work here. We have to split the middle. Minus 1U minus 20U. You could put those in either order. You'll get the same at the end. Okay, so out of the first pair, I can get a U, which leaves behind a 4U minus 1. Copy down that minus sign. And they have a 5 in common, leaving behind a 4U minus 1. They match. That means we had the right magic numbers. We factored the GCFs correctly. Everything is good. 4U minus 1 is one of my factors. U minus 5 is the other. Don't leave U in your final answer. Got to put x squared back. So 4x squared minus 1 and x squared minus 5. Is 4x squared minus 1 factorable? Yeah. Yes. Difference of squares. How does that factor? Okay, and then is x squared minus 5 factorable? No. 5 is not a perfect square. He can be in the final answer. So we got 2 linears and a quadratic that wasn't factorable. We'll label that as not factorable. Only non-factorable quadratics are allowed to stay in the final answer. And when you type that in, you would just use a little caret for that factor, x squared. All right, so 4 terms is factored by grouping. 3 terms is use substitution. Now we're going to talk about what to do for 2 terms. Okay, so just like when we're factoring a 2-term quadratic, we have difference of squares. We also have a difference of cubes. That's why you need to have your perfect cubes memorized. Sum of cubes this time is also a thing. Okay, sum of squares is not, sum of cubes is. Okay, so once you realize you're working with a sum or difference of cubes, you're going to use the acronym called SOAP. S-O-A-P, SOAP. Okay, it stands for same, opposite, always positive. Okay, so if you are working with minus, your first sign is going to be the same, then opposite, so plus, and then always positive, put a plus sign. If you're working with a sum, same would be plus, opposite would be minus, always positive. So SOAP helps you remember which way the signs go. Okay, this A and B is the cube root of your originals. Okay, so let's just do some examples. Okay, so this first one, the first thing I do is figure out what the cube root of each one is. Okay, so the cube root of x cubed is just x. The cube root of 27, 3. Okay, so this x is our a value, this 3 is our b value. I rewrite it like that so I can look at what the x and the 3 are. After I rewrite the problem to look like this, I do one small set of parentheses for the linear factor. You're going to have a linear and followed by a quadratic. And then I do a bigger set of parentheses for the quadratic. Okay, you're always going to be left with a linear and a quadratic that's not factorable. So it's going to look like you can factor this quadratic. It won't be factorable. So that's why a lot of people love this method, because you're done at this step. Okay, and so I fill in the signs first. Okay, so same, opposite, always positive. Once you've put those signs in, you're going to ignore signs for the rest of the time. Okay, and then this x goes right here. This 3 goes right here. That's going to be your linear factor. For your quadratic, this is what I say in my head when I'm doing these problems. Square the first, gives you x squared. Square the last, gives you a 9. Multiply the 2 together, gives you a 3x. Square the first, square the last, multiply the 2 together. That's what this a squared, b squared, ab means. Okay, and then ignore all signs when you do that. You already took care of what the sign should be. Okay, and then you're done. So if you know your perfect cubes, these are really nice. Okay, over here, what is the cube root of 8x cubed? There you go, 2x. What is the cube root of 125? Good. Okay, so 2x is our A. 5 is our B value. So small set of parentheses, big set for the quadratic. Same, opposite, always positive. The 2x goes here. The 5 goes here. Square the first, including the 2, and you get 4x squared. That's a common mistake, is forgetting to square the 2. Okay, square the last, and you get 25. Multiply the 2 together, and you get 10x. Ignoring all signs because we already took care of it. Okay, and you are done. Also, remember that trick of multiplying the first two terms. 2x times 4x squared is 8x cubed, just like we started with. That way, if you did accidentally forget to square the 2, you would catch your mistake right there. All right. So these are very similar to what you will see on your test. Here are some spicy ones to really make sure you understand the method. Mr. Daugherty came up with these, not me. Okay, so first things first, there is a GCF. There's an x cubed sitting here and an x9 sitting here, so you can factor out an x cubed right off the bat. So it's going to drop both your exponents by 3. Okay, so that leaves me with 27, don't write 2, 27 x to the 6 minus the 64, because we factored out the x cubed. Okay, leave that x cubed alone. We'll bring him back for the final answer. Looking at 27x to the 6, what is the cube root of 27? And what is the cube root of x to the 6? Okay, you're thinking about 2 times 3 would get us back to the 6. So it's actually x squared. You basically divide when you take the cube root. You divide the exponent. Okay, so 3x squared is our A value this time. And then what is the cube root of 64? Very good. Seeing why those perfect cubes are very important to know. Okay, so we are ready for our small set of parentheses, followed by our big set of parentheses. And let's go ahead and write the x cubed in front since we know we need him in the final answer. All right. So same, opposite, always positive. The 3x squared goes here. The 4 goes here. Square the first, and what do you get? 9x. If you square, it's 4. Because it's 2 times 2. Square the last, what do you get? Multiply the 2 together. 12x squared. Y'all just factored a degree 9 polynomial. All right, looking at number 4. There's an x6 here, but then there's a y cubed here, so there's not going to be a GCF we can factor out. Yeah.
So even if the 4 is negative, you would still have the positive 4.
Ignore all signs. We take care of it when we do SOAP. SOAP takes care of the signs. All right. So no GCF here. So what is the cube root of 125x to the 6? 5x. Very good. When you have two exponents, you multiply them. Okay? And then what is the cube root of 27y cubed? 3y. Okay? So that 5x squared is our a value. That 3y is our b value. Small parentheses, big parentheses, same, opposite, always positive, and now we ignore all signs. Put the 5x squared here, the 3y here. Square the first, and what do you get? Very good. 25x4. Okay, square the last, and what do you get?
9y squared.
Very good. 9y squared. Multiply those two together. Yes. You cannot combine the x squared and the y into some kind of cubic. It doesn't work that way. Leave them separate. And you just factored a degree 6 multivariable polynomial. All right. So I'm going to let you do 1 through 6 on your own, but let's go ahead and label which method we would use for each one. These are similar to what you will see on your test. They are all degree 4 and degree 3. So your job on a test is to recognize which special case it is. So looking at number 1, it's a degree 4 polynomial. Which method would I use? Use substitution. Okay, it's got 3 terms, and so I'm immediately thinking use substitution. The first exponent is twice as much as the second, and there's a constant. So that screams use substitution. What about the second one? Okay, grouping. There's 4 terms, and you can already tell that the ratios are going to work out. 5 to 5, -3 to -3. Okay, what about number 3? Very good. U sub. 4 is twice as much as 2 for the exponents, and the last term is constant. Okay, be careful on number 4. That is not a U substitution. There are 3 terms, but the first exponent is not twice as much as the second one. And so what you'll notice about this degree 4 polynomial is that the last term is not constant. Anytime the last term is not constant, that just means there's a variable distributed all the way through. And so this time there's an x squared we can factor out right off the bat. Okay, and so if I factor out an x squared, it leaves 8x squared minus 10x minus 3. And that's just a quadratic. Okay, so if I take any quadratic and multiply it through by x squared, suddenly you're working with a degree 4 polynomial. Okay, and so you would just factor that the way you've been factoring quadratics since unit 1. Okay, it's not even one of our special cases for degree 3 and degree 4. Just a GCF. Don't forget to write him in your final answer. Okay, what is number 5? That's difference of cubes. We'll just write SOAP. Anytime it's a sum or difference of cubes, we'll write SOAP. And the last one is grouping. 4 terms, grouping. All right, so you're going to do these 6 problems, and then you are going to submit a PDF to Canvas. And then once you do that, I think I have the key linked. So you will click next, and you will be able to check your answers right here.